Hi, good morning, everybody. Welcome back to CS182 282A. So today we're going to get into generative adversarial networks. So as most of you know, this is a very, very powerful method for generating synthetic images, synthetic text, a variety of media. And it takes a different approach from what we talked about last time. Um, so last time we were talking about variational autoencoders that attempt to transform from a natural image or natural media into some kind of a code, Z, and then back out again to a new form of output, X prime, that ideally is similar to X. But it's a probabilistic method. So in fact, the Z generated is random. It's not deterministic in terms of X, and similarly the X prime is random given an X. All right, and so you can think of that as data compression and decompression. The code is, in a sense, very compact and minimal in terms of describing the image, so that captures just the essential elements of the image. Okay, so the approach we took was to use probabilistic networks. So there, an output variable X is a conditioned on a variable Z, and the network has some parameters theta. And the model shown here, excuse me, let's see, so we have the basic parameters theta of the network, and someone asked last time about why the arrow goes from theta to Z. It's just because sometimes the generator itself is parameterized, but in most networks in practice it isn't. It's just a Gaussian random generator. But the network itself, the network, is p theta. It's taking Z as input and producing an X. There are n of those samples in general. They're all parameterized by the parameters of the deep network. So similarly, we can create another deep network, Q of phi, that goes back the other way. But remember that both of these networks are probabilistic. So they both, non-deterministically produce samples given their input. Oops. Okay, and it's an autoencoder because it goes from an input to a code back to an input. Okay. We also talked about autoregressive models, and one of the simpler examples was pixel CNN, where basically you have a convolutional network that produces a single softmax output given an area of an input image, and you can apply that recursively to generate an output image pixel by pixel. And some of the variations of that include the image transformer, where you take either short rows of output produced from some context, or you can even produce square or rectangular blocks of output given a bigger input context. And it's autoregressive in the sense that the output's conditioned on some of the input. Okay. Let's see. So these methods try to generate some kind of distribution over the inputs or the images, PX. They generally are not very realistic because deep networks are not really very good at modeling probabilistic distributions. At least they're not good at directly modeling densities. And especially if you use the standard variational approximation, which is to treat the distribution as basically a white distribution or a Gaussian distribution about a mean, that's in practice very far from what the real posterior distribution looks like. So the effect is really adding a lot of variance or noise to the images, and they don't look very good in general. So if you imagine trying to do something that's more direct, you would like to compare the images themselves instead of the some kind of loss based on the Z parameter, and basically model the process of a human discriminating between real and synthetic images. And okay, so my update slide probably should have come a slide earlier, but anyway, so assignment 3, we pushed back the deadline until after spring break, so that's now due on Tuesday. after spring break. So for midterm 2, we're sort of conscious that some people may have gone home already or trying to go home soon. And so since there's a lot of complexity with dealing with different time zones and poor network connections wherever people are, we've actually dropped the synchronous midterm 2, and we're replacing it with 2 take-home quizzes that you can do over a period of days. They're intended to be, short quizzes, roughly 1.5 to 2 hours, but you can take more time. So look at the course homepage for details of those. And we want to make sure you're doing okay. If you have any particular challenges or issues, please raise them with the staff. And otherwise, this would be a good time. Are there any questions so far? You remember, you can either raise hand from the participant list or you can type in the Zoom chat. No? Okay, not so far. All right, we'll keep going. Okay, so several issues with the variational autoencoder. So first of all, it's trying to maximize the likelihood of the data. That's typically what a good model will do. It's, that's saying that the distribution that it generates is close to the real data distribution. But it can't do that directly. There are some terms in that expression that are not computable. So we use this evidence lower bound, which you can write as a KL divergence. And it's comparing really the code distribution of Z between the kind of backward going function or the encoder function Q and the forward going function P. It actually compares it's a little strange if you really think about it. It's comparing one conditional distribution and one joint distribution. But anyway, it's not comparing the images. That's the point. And it also needs this density estimate for some part of the evaluation. And that's a pretty gross approximation. In general, Z could have a very complex distribution given X, but in order to make this tractable, in other words, be able to integrate it for one of the KL divergence terms, you have to write it in a very simple form such as this, so you can compute the KL divergence. Okay. So weaknesses of VAEs is that they need this density estimate for Q. And so if you think about it, graphically on the left here, it's a simulation of what that might look like. If you have an actual distribution of Z samples that looks something like this, kind of this diagonal distribution, the best you can do with a typical variation approximation is generate an ellipsoid of distribution, Gaussian ellipsoid, that's axis aligned here. It's a little bit like the approximations that we saw earlier in RMS prop or AdaGrad, where you compute a coordinate aligned approximation to the variation of the gradients. So this, especially in high dimensions, can be very, very far from the actual distribution. I'm sorry, the actual distribution here can be very, very far from what the VAE can approximate. And a general consequence of that is that the approximation with some kind of normal distribution actually has a lot more variance or noise than the actual samples do. And introducing that extra variance tends to blur the images. Okay, so what we would like to do if we could would be avoid those approximations in the variational expansion of the marginal distribution of X. So, and we'd like to also compare, when we're training the generator, we'd like it to be kind of optimizing some kind of difference between real and synthetic images in image space. And we'd like to remove, if we can, the constraint that the generator has to produce density estimates for X given Z. Okay, so if we have a generator G sub theta of Z, then And I mean, it's implemented as a conditional generator. So we can integrate out to get the marginal. We had that expression last time. So the marginal, I mean the marginal removing Z. So this is just the likelihood of the data. And in addition to the synthetic distribution, P sub theta of X, that's what we're generating, we could have a real distribution, which is just the density of the images, real images. So we're not saying we can actually compute either of these given X, but we can generate samples from either one of them. So there's another kind of divergence that's actually built on KL divergence, which is called Jensen-Shannon divergence. It can be defined between anything, but in the case of the synthetic images and real images, it looks like this. So right, it's Jensen-Shannon divergence, excuse me, between the real image distribution, the synthetic image distribution, and it's got two terms. One of them is KL divergence between the real images and the average distribution, which I'll define in a minute, plus half the KL divergence between the synthetic images and this average images. And the averaged images are just the average of the two distributions. Or if you want to think about it, that's the same as alternately sampling from real and synthetic images. So this is a sensible measure because it's symmetric actually, whereas KL divergence is not symmetric. This one is. You can clearly swap the real and synthetic distributions, get the same formula. And then if you write it out, write the KL divergence out as expected values, then the first one is an expected value over the first distribution of this ratio here. And the second term is expected value over the synthetic images of this ratio here. So far, if we wanted to estimate this, we have an expected value over some samples, which, you know, typically we get a good and unbiased approximation by just sampling from this generator. Sorry, this is real images, sampling from the real images. And here we can get, you know, a good approximation to this expected value by sampling from the synthetic images. But what we're left with is somehow estimating these two ratios, in fact, the log of those ratios. So there we need to do a little more than just take samples. But luckily, there's a very convenient way of doing both of those. All right, next slide. Yeah. And, you know, just to not lose the context, what we're trying to do here is generate a metric or a comparison between the real and synthetic images. And we're using this Jensen-Shannon divergence to do it. So we can write it out like this, once again. And yeah, as I just said, we can approximate the expected values easily enough by sampling. And we now want to estimate, though, these densities, or actually, to be more precise, we want to estimate density ratios between these two distributions, real and synthetic, and then the average distribution between them. So it turns out that if I build a classifier that classifies real and synthetic images, its softmax output actually has this form. So if the classifier is trained to assign a 1 to real images and a 0 to synthetic images, and it has a softmax output, a perfect classifier would actually compute this density ratio here. And we already know that deep networks make very good classifiers. Okay, so now if we define this discriminator as, well, almost actually no, I'm sorry, it is computing almost the density ratios that we want. There's just a factor of 2 here because we want this density ratio here. This is the density of real images over the average of real and synthetic. And we just multiply by 2 and that removes the half. So a normal classifier generates something which is almost what we want. Okay, so now if we write out the Jensen-Shannon divergence again with samples, and also the log of now this slightly tweaked classifier output, and then take expected value over synthetic samples of the log of, for the synthetic samples, we want p theta over the sum, and that's just 1 minus the discriminator output. So 1 minus d puts p theta on the top over the sum. So in other words, this is still the previous term, which was p of theta over p theta plus p of real. Okay, and then this term here ends up, giving us a log 2 at the end. So hopefully what we've shown is that what we want to do is compare real and synthetic images, and what we've found is that we can estimate the difference between those two distributions by basically taking some samples of real images, evaluating the output of a certain classifier, taking the distribution over synthetic images, and computing, take the same classifier on those images, but do a 1 minus its output. And yeah, and that if you take enough samples of both sets, then this whole term will be an estimate of the difference between the distributions of real and synthetic images. So it's all differentiable, it turns out. And so you can use this criterion as something that you would like to minimize between the two sets of images. And in that way, the two sets of images should have very similar distributions. Okay, are we doing all right so far? Any questions so far? Not yet? Okay. All right, and just simplifying a little bit, since we're optimizing and taking gradients, the constants don't matter here. And, by scale factors similarly don't matter, so we can just remove those terms and now treat this, what's left, as the criterion that we want to minimize. Okay, and there it is, a little bit simpler now. So, so we need to train d sub phi of x. I'll start calling that a discriminator. If we can train that, and if it's continuous and differentiable, then the expression above can be accurately estimated by sampling from the distributions and then evaluating the classifier output, or rather the log of the classifier output. Okay, so in a moment we'll make a remarkable observation, but first, if we train a classifier in the normal way, we would use cross entropy loss, and that means that we would take samples from one distribution, and yeah, I guess you have to believe me that this expression is the cross entropy loss for classifying these two samples. It probably, hopefully it looks familiar. I mean, again, this is the log of, let's see, the probability of real images over real plus synthetic, and this term here is the probability of synthetic over real plus synthetic, and that's what the classifier optimizes. That's what it should output. And cross entropy is, basically the distribution of the, let's say, true samples times log of output, false samples times log of 1 minus output. So anyway, that is the cross entropy loss. So the classifier, remarkably, hopefully you can see it already. If not, yes, we just did see it, the same formula basically in the line above. So in other words, the terms in the loss between the two distributions, the Jensen-Shannon divergence, are the same terms in the classifier that we want to train d sub phi in order to compute this loss. So the only difference is that there's a minus sign in the second expression in the cross entropy loss, and there's a plus sign in the Jensen-Shannon divergence formula. So that's a little strange. We can't really optimize both things at once, but it's still okay because we can do an kind of an alternating optimization where we optimize one and then optimize the other. And that probably sounds weird because we have to be a little bit careful about what we're optimizing over. Here, because it's a classifier, we're actually trying to tune d sub phi. So here we're going to minimize the classifier loss, which means we're going to tune over phi. Up here, we're trying to generate the best samples, which means we're tweaking p sub theta instead. So although those two losses are the opposite of each other, it still makes sense because each one is optimizing a different set of parameters. All right, so we want to minimize the cross entropy loss. That's what we're using to train the discriminator. We can compute its gradient. And well, I mean, this is just a quick proof that when we have optimized with respect to phi, you know, it means that this gradient with respect to phi is 0. And there's the formula for the gradient. And from the formula for the gradient, you can see that the best classifier actually satisfies the formula that we want it to. So this is just a proof, a short proof that an ideal classifier would give us the exact density ratio between real and sort of average images. Okay, so yeah, so now we're trying to sort of do this alternating optimization. And here we've actually put both steps of optimization into one formula. Although in practice it's done by 2 different steps. But it's still achieving the goal of basically minimizing the Jensen-Shannon divergence for the image synthetic, for the set of synthetic images, and it's simultaneously minimizing the cross entropy loss over phi, but the cross entropy loss is actually minus this formula. So it's equivalent to maximizing over phi, this expression here. Okay, is that making sense? We've gone from 2 minimizations where one of them has the negative of the thing being minimized to a single formula where we're minimizing and maximizing over the parameters, because maximizing over the parameters of this is the same as minimizing its negation. Okay, all right. So yeah, so in other words, yeah, the formula above is the negative of the cross entropy loss, this thing inside here. So if you want to think about it, we're training the generator to actually maximize the cross entropy loss. In other words, it's trying to fool the discriminator, and the discriminator is trying to sort of maximize the Jensen-Shannon divergence, which is a good thing to do. It's trying to classify the samples as well as it can to highlight differences. And that's an adversarial training because you have effectively two agents, and each agent has control of a separate set of parameters. One is trying to push that formula up and one's trying to push it down. Okay, so again, has a 2-network architecture. So there's a generator that's generating images from some Z, and then a neural network discriminator that's comparing the 2 sets of images and, you know, roughly speaking, trying to approximate a human critic. And the GAN learns transformation from some kind of random sample distribution P of Z, typically a Gaussian, to the actual image space. Okay, so a very interesting sort of property of the adversarial networks, of the GANs, is that if you had to build fixed discriminators, the deep network that's the generator, because they're very clever at optimizing what you give them, would probably do a good job after a while of fooling the discriminator. But the discriminator is learned concurrently along with the with the generator, and the discriminator always has an accurate label because it always knows whether samples are coming from the generator or from real images. So if there's any distributional difference, it's pretty good at learning that and then still separating the two sets and saying but it's also because we're optimizing those expressions with gradient terms, whenever the discriminator succeeds in discriminating, it provides a signal back to the generator that allows it to do a better job of synthesizing. Anyway, so formally, it's a two-player game, which, you know, two players, one is trying to minimize something, one is trying to maximize. And so with a bit more formalism, you can show it has a Nash equilibrium. So that's the point at which both players are doing as well as they can. All right, so any questions so far? Okay, so the generation network learns the transformation from some Z to the target distribution. Okay, and yeah, we're not trying to model a posterior likelihood. So one advantage that we have now is that we're only trying to generate individual samples. And in fact, we can do it deterministically. So given a sample from the latent space, we run that through a generator and it, generates a single output image. The discriminator, on the other hand, measures the goodness of the generator by comparing it with real images and trying to classify them. And okay, so that's the other network, and we already argued that gets trained actually to maximize the Jensen-Shannon divergence, or effectively fool the generator. Okay, so yeah, so as I said before, the formula itself that we came up with is differentiable, and if the discriminator is a simple deep network, the classifier, let's see, the generator, I'm sorry, will actually get a signal from the discriminator by backpropagation. We'll see that in a moment when we look at the formula again. So that's important because it means for most discriminators, you can actually train GANs just by backpropagation. It's not always true though. Sometimes the discriminator, for instance, if it's say a transformer network, and a transformer network that's actually generating symbols by sampling, it won't be differentiable. But anyway, many other models are. If either discriminator or generator are not differentiable, it's still not terrible because you can still use the reinforcement algorithm to do the optimization. Okay. All right. So bringing it all together, this is a better graphic to understand how the gradients flow. So we have a distribution of real images over here. And those are fed in one at a time to the discriminator. And the discriminator is trying to output real, a 1 for real and 0 for fake. On the other side, we have synthetic images. So we take a random noise sample, pass it through a deterministic deep network, produces an image, and then we provide that to the discriminator. Now, notice that if the generator is generating this image differentiably, in other words, if the image is the output of some deconvolutional stage of the generator, we can actually backpropagate a loss signal all the way from the output through the discriminator and through the generator. So in other words, everything's differentiable. And as we see examples of generators, that's going to be the case almost always, that the actual generator produces the image as the outputs of some differentiable layers. And because of that, and because the discriminator has also got differentiable layers, we can propagate gradients all the way through. And that makes things a lot simpler to train this network. So is that clear? Okay, hopefully so. Okay. Yes. So this two-player min-max game in practice, it's going to be implemented by alternately optimizing the discriminator and then the generator. And again, we've said this a couple of times. It has two terms. This is a sample, take samples from the data distribution, compute the log of the discriminator value output, and then add the term that comes from the synthetic samples, and then apply a log of 1 plus discriminator applied to generator. And so this is where the gradients flow. If the discriminator is a differentiable network and the generator is a discriminable network, then those two allow the gradients to propagate. Okay. All right, and here it is as pseudocode. So for case steps, you sample a mini batch of noise sample Z from the noise prior, and also sample a same size batch of real data from the set of real images that you're training on. So you update the discriminator by, let's see, ascending the stochastic gradient here. Yeah, so this is the Jensen-Shannon divergence. So you're trying to maximize that. And yeah, so both, I mean, since you're optimizing, I see. So here, yeah, it's a little confusing. The parameters of the discriminator in this pseudocode are theta D. We were using phi, but anyway, it's optimizing over phi in our notation. So in other words, optimizing the discriminator. Let's see, and this, well, it's perhaps a little bit not obvious, but this is being done on both sets of samples. All right. Then for the generator, it's only necessary to use the synthetic samples because the generator, if you notice, only appears in one of these two terms. So there's no need to compute this term for the generated samples. So in fact, you only need to compute the second term. So that's what this is here. And you compute it with the synthetic samples and then optimize the parameters of the generator. Okay. So it's just making computational what we were talking about so far. And although we're doing nominally a kind of a game, mini-max game, we're basically giving players one turn and then another. So we're alternating between the two players as we do these optimizations. All right. So yeah, and this is just reiterating that, we have this kind of min-max game and we're implementing it with, actually here it's max min, I guess. Okay. Yeah, so it's a little tricky to actually implement in typical toolkits because you've got to be very careful that only one set of the weights, either generator or discriminator weights, are being updated in each step. Okay, still any questions so far? Okay, so here's the generator loss term. It turns out that there are a variety of advantages to optimizing this term instead. I just keep going because it's not going to be very, excuse me, not going to be very obvious why. But the second formula, it gives you better gradients when the samples are bad, and the traditional model gives you good gradients mostly when the samples are good. So when the samples are good, you're going to have a discriminator output of about 0.5, because that means that the discriminator is being fooled and it can't really guess. When the samples are bad, the discriminator though might have a very it will discriminate easily, meaning its error is small, and so then you get weak gradients. So this approach generally works better. Okay, let's see. Yeah, and so our generator is just a neural network. We'll describe the architectures in a moment, but our goal is to make that differentiable so that it's easy to train the entire system. So yeah, the very influential first paper on GANs by Bengio and Ian Goodfellow and others came out in 2014, and you can see some samples of its output here. And originally they only applied it to the MNIST dataset and also Toronto Faces dataset. So not bad. I mean, it seems to have lost some of the blurriness of the VAE approach, and in particular, the digits look really pretty good. But that was really just the start of the revolution in using GANs, and so huge number of papers built on that. But I think early on people recognized fundamentally, but this is a better way to go, because by using basically deterministic generators and deterministic classifiers, you're really leveraging the power of deep networks. You're really leveraging what they do well, rather than what they struggle to do, which is modeling probability distributions. All right. And yeah, it didn't do so great at all on SciFire, on these natural color images. So in some practical tips for training GANs, there's a fine balance in optimizing the discriminator and the generator. One has to be careful that neither one of them gets too far ahead of the other. In other words, it's not good if the generator is always fooling the discriminator, because then the generator is not receiving any advice from the discriminator. And it's also not good if the generator is always fooling the discriminator, because again, in that situation, the generator doesn't really know how to improve, the discriminator doesn't know how to recognize things, which means that the generator again doesn't get any signal. So in practice, that alternating optimization that we described might have some guardrails on it to make sure that the discriminator doesn't become have either too high or too low a loss. And here is a sample of some of the papers since the original GAN paper. And yeah, so there's many ideas here, but we're gonna give a sample of some of the important ones, also big GAN. Okay, so the original GAN paper left open what the architecture of the generator is. Okay, so we have a question from Mandy. Go ahead.
Oh, I think there's a question at the chat.
So I'm sorry, I just realized I didn't have my audio on. Would you mind repeating the question?
Oh, sure. It's Kevin saying, can you explain the practical side note again?
Oh, well, the practical, I mean, there were several practical issues. The first one was the use of the log of D instead of log of 1 minus D, and the reason there is it gives better gradients. The other practical issues are basically keeping the discriminator output in a good working range so that it's able to provide good advice to the generator. So, you know, in other words, it's a two-player game, and the game doesn't work well if one of the players is winning all the time. Mm-hmm. So if the generator is always fooling the discriminator doesn't know what to do, there won't be a gradient in that case going through the generator to improve it. If the discriminator gets too far ahead and it's always classifying perfectly, you'll find that there is a gradient, but it may not be very, it's may not be very good for the discriminator. And in fact, it tends to vanish if the discriminator output is very close to 1. It's just a property of the softmax. So generally it works best if the discriminator is doing a little bit better than 50-50. And so in order to maintain it there, you can slow down training of the discriminator or slow down training of the generator and have, allow the other player to have more moves, if that makes sense.
Yeah, so are you saying discriminator is the one that tends to get left behind in
It can be either player can get left behind.
Okay.
It's not good either way.
Okay, thank you.
Yeah. So let's see. So so we want to then now explore what makes good generator architectures. We only have to build deterministic networks to generate that take random inputs. And one of the first very successful architectures was the DC GAN, which is a deconvolutional GAN. And I mean, the name's somewhat confusing, but it uses convolutional layers that have fractional stride, or kind of upsampling. So we saw those before, for instance, in UNet architecture. So they're progressively going up in resolution until they generate a full resolution image. Okay. Yeah, so the more correct description is fractional stride transposed convolution. Yeah. Yeah, all right. I think we already understand what that is, hopefully, from earlier. And there were some other sort of guidelines in the DC GAN architecture. The pooling layers are replaced with strided convolutions. They use batch norm for both generator and discriminator. No fully collected layers, excuse me. Use ReLU in the generator, except the very last layer, which has a 10H. And they used leaky ReLU in the discriminator, I guess, to provide smoother gradients, probably. Oh, Mandy, do you have a question still? Or maybe put your hand down?
Yeah, have to.
Sure. Okay. All right, good. So, yeah, so now if you look at some of the outputs from DC GAN, they're starting to look much more impressive than the earlier results. They, at least at this resolution, they look really awesome. If you zoom in, you'll find that they're not as really as good as they look here, but they're getting both more local and global properties of the images because they're doing this upsampling. They seem to generate kind of good multi-scale output. Yeah, and also DC GAN, they were able to train fairly high, well, I guess no, I shouldn't say high resolution yet. They're using crops from ImageNet. But still, significant improvements over the original GAN paper without really changing the main architecture of the GAN. They just improved the generator. And interestingly, so DC GAN now exhibits the kind of additive latent space behavior that we saw with word2vec. So you can do algebra on families of images. So for instance, here we have a set of images of a man with glasses, and you can basically compute a difference vector from the set of images of men with glasses from the set of images with man without glasses. And then if you add that to a set of images of women, you get the output then is a set of women with glasses. Is that making sense? So again, remember that yeah, so there's a little trick here. You have to, yeah, all right. This is a little, yeah, there's a little bit of sleight of hand going on here because strictly speaking, the generator doesn't have the ability to compute the code Z from the images. So there was a little bit of trickery to produce these images, but the observation is still accurate nevertheless that you can use the Z's as latent vectors. Okay. And that observation is very relevant to the next topic, which is rather than just generating images of anything, which is so far all the GAN can do, all it can do is produce a random sample of an ImageNet image if it's trained on an ImageNet. So that might be a horse or a dog or a car. But generally speaking, when we're synthesizing images, we want to synthesize images of a particular class. So we would like actually to make, let's see, there's a discriminator. Yeah, unfortunately oh no, this is fine. Yeah, the generator, excuse me, the generator is producing a sample of an image that's conditioned on the class label this time. So we still have the random vector Z, but we make the generator conditioned on Y. And also the discriminator gets to see what Y is, because it's important for it to accurately, it can do a much better job comparing real and synthetic images if it knows what the class is. So yeah, let's see. So the Y is the green dots here. So when you're producing samples of images here for the discriminator, you produce pairs of both the image but also its label. And the discriminator gets to look at both of those before it's making a decision about whether, whether it's real or synthetic. The generator, similarly, when it's trying to generate something, it gets to see the random Z input, but also the class label that tells it what kind of image it should be generating. So, and otherwise, the networks are fairly similar to what we saw before. They're just getting this extra information about the class label. Is that clear? So it's conceptually pretty simple. Just add a class label as part of the input to both models. Okay. So now you can see different rows of the output of this generator correspond to particular classes. So it's told to generate zeros or ones or twos or threes. And this is the output in each of those cases. Yes, so any questions on the CGAN, that's conditional GAN? All right. So in many cases, it's beneficial to do this slightly differently. In a CGAN, both the generator and also the discriminator get to see the class labels Y. In an ACGAN, this is a slight variation where the generator still sees the class labels and tries to generate them, but the discriminator, instead of being trained to just discriminate and produce a true-false output, it also produces the class label. So now it's fed the class labels during training, but it's trying to produce them as an output. Yeah, and I think this is just the math of what we described before. It's not super important, as long as you understand that now the class label is going to be an output for the discriminator. All right, so so an ambitious version of CGAN is doing text to image generation. Actually, also, you could view image to text as a kind of a GAN task as well. So in fact, classification or labeling can also be, implemented as GANs, as conditional GANs. So it's not too much of an extension of what we described. The main difference is that, at least in this first implementation, they took a text description as a sequence, ran a recurrent network on it, and in addition added the random component, and that produced a set of inputs to the conditional GAN image generator. And similarly, you have to provide a similar conditioning on the output. And so that's typically done with another recurrent network that provides input just before the network's going to produce an output. So at high level, it's still like the CGAN from before, except that it's taking sequence data and running it through a recurrent network to produce a single fixed dimensional latent vector on its output. Yeah, and it's a little more complicated because you have to have sequence losses on the input and output, but otherwise it's conceptually very similar to C-GANs. So basically, conditional GANs really can solve a lot of really pretty complex generation tasks. And the conditioning doesn't just have to be a discrete class, it can be a text string or some other kind of media input. Okay, and here are some examples of the outputs generated from this synthesizer. They're a little bit small, but you can see a group of people on skis stand on the snow, and there's the there's the output there. Sorry, this is ground truth, and here are some outputs generated by the network. Let's see, a sheep standing on an open grass field, ground truth, and then some example sheep standing on fields. All right, so it's really doing a pretty good job, and obviously with that kind of description, you can generate a really rich set of images. So we're going to move on from a few of the GAN architectures to more general issues around GANs. So I'm just, again, waiting, are there any questions? All right, so so there's a few challenges in training GANs that relate to the complexity of doing this alternating game. So let's work through some of those. So one of the most common problems is called mode collapse. And it arises when you have collections of media or images whose distributions have multiple modes or peaks. So in this case, you'd like to generate a distribution of temperatures, and that some of the places you have are the South Pole, and then Alice Springs is a very hot place in the middle of Australia. So your generator should be generating examples from both distributions, in fact, about 50-50, both of those peaks. So let's suppose, but it's generally hard to generate multimodal data. Somehow you've got to split your latent space and create these two peaks. So assuming your generator at first, very likely it will generate most of its outputs in one of the modes, say the South Pole. The discriminator then will have a lot of success if it guesses that all of the Alice Springs temperatures are real, because currently the generator can't produce them. And for South Pole, maybe it guesses 50-50. But now the generator switches, but the generator is constantly improving to try to fool the discriminator. And that if it starts now switching and producing all of its samples in Alice Springs, they will all fool the discriminator because the discriminators learned to call those real images. And now the discriminator sees that the mode has switched to the other mode, and therefore it will switch its decision and give assign those 50-50, but assign the South Pole as all real. So you can see these players are kind of in this unstable state where they're kind of fooling each other on alternate rounds. And this is a fairly common phenomenon in practice, and you can see some examples here. So there's a variety of solutions. One of the first ones was using experience replay to kind of average over time, so that you're if substituting an older version of the discriminator generator, so they really can't have this dynamic behavior. And yeah, so that's, I think that's intuitive why that would work, and it does. So let's see, the alternate training scheme. Yeah, because we have this very long a derivative path that goes through the discriminator and through the generator. We've already hinted that those gradients can be very big or zero, sorry, very small or zero, depending on the training context. So one way to make things better and also deal with the mode collapse problem is to use what's called a Wasserstein GAN, or WGAN. So the WGAN replaces the Jensen-Shannon divergence between real and synthetic images with something called a Wasserstein distance, or Earth movers distance. And it's called Earth movers because if you think of the probability distributions as piles of dirt, it's the amount of movement of the dirt to produce one distribution from the other. Okay. So we have two distributions. They're going to be the real and synthetic image distributions, and we want to compute how similar or different they are in terms of the effort to move mass, if you like, probability mass, from one to the other. So on this slide, we have these two distributions. Let's just assume they consist of samples. Then here's an initial density P, and there's a Q density, real and synthetic. We'd like to determine how much it costs to convert the real distribution to the synthetic one. So on the right here, there are two plans. One plan here is to move this chunk. Let's see. One plan here is to move this chunk up here. Yes, move this chunk over to here. So it's shown here, move this part to there, which will produce the QX. And the total cost of that is that you've got to move the purple region. Another way to approach that is, well, obviously this is an inefficient way to do things, but you could move some Earth from X2 to X1 first, making it even bigger, and then move that chunk of Earth from X1 to X2. So in that case, you get a bigger distance. Anyway, so the Wasserstein distance is defined as the minimum across all possible plans of the amount of Earth that you have to move. Is that intuitive? So the different ways of moving the probability mass around, the Wasserstein is the quickest one. Okay. So for an image generation task, we're measuring the distance between the synthetic distribution and the real distribution. So it's really pretty challenging to do this. And in fact, the real implementations of Wasserstein GANs are approximations, pretty rough approximations, but nevertheless they work. So our goal is, instead of now a discriminator, because the discriminator was estimating cross entropy loss, which was related to Jensen-Shannon divergence, now we want some kind of critic function who's such that differences between the critic function on two distributions approximate the Wasserstein difference. So this is a little tricky, but we're actually now computing a difference. So you see, we compute this critic function on the real samples, and then the critic function on the synthetic samples, and just take the difference. So that seems kind of magical, because it doesn't even look like a metric, but it behaves like a metric. So it does turn out that there are certain critic functions such that computing the difference between the critic functions on real and synthetic data does in fact approximate the Wasserstein metric between those two distributions. So we're not going to prove that, but it does turn out to be true. All right, so now we have a similar looking minimax problem to the traditional GAN. Our generator, our generator is trying to maximize the score, which is going to lead to a bigger difference between the real and synthetic data. It's trying to maximize this, which will lead to a smaller difference when we maximize this term, we generally, well, we're minimizing this term. So it'll lead to a smaller difference between the real and synthetic. And then the other actor, effectively there isn't a discriminator, but there is an FW, and FW is trying to maximize its estimate of the Wasserstein distance. So it's similar to before. This is effectively a discriminator-like function, trying to maximize this difference. And then a generator is trying to maximize this term, which means minimizing that term. Okay, so far so good. All right. The nature of Wasserstein GAN is that it provides very good gradients across a wide range of images, both good and bad ones, and early and late in training. And it provably avoids mode collapse. And there's quite a lot of theory and constraints on how you do it, which we won't go into, but it is one of the more successful methods for training GANs. Let's see, okay. There should have been a slide. Let me just, not sure what happened. There was a slide with the actual pseudocode for WGAN. It's pretty simple. It's basically just optimizing those two functions in an alternating way. All right. So, okay, so there are a few more ideas to address some of the challenges. So we're still talking about these challenges that we identified on a few slides ago. One of them is that images can have structure at different levels of detail. The idea of a progressive GAN is to start with a very simple generator, but still compare its generated output to the real images, and then progressively refine the image. And the idea there is that you hopefully get the macroscopic structure right first, and then get the microscopic structure done later. But in contrast to doing kind of an end-to-end optimization of the final product, you're directly optimizing and applying loss to the incremental stages, but then retraining to tweak them. So the authors got some very nice results on synthetic faces on a face data set, and also on a larger data set. I think these are ImageNet images, not completely sure, but you can see the images are now starting to be quite high res. Some of them look very realistic. There's still a variety of artifacts. You can see this is a two-headed horse here, but mostly the horses have one head. The vehicles, mostly good. This bicycle has two sets of handlebars, but otherwise it's pretty good. So the global to sort of local structure idea seems to be working pretty well. Okay, another approach to GANs is Big GAN, which is just really scaling things up and using state-of-the-art residual blocks, tweaking the architecture in a few other ways. And actually, with careful architectural design, they found that you didn't need the progressive GAN idea. You could just train end to end. And here are some of the synthetic images that it produces. And well, a lot of good things are happening. So you can see the wolf image is anatomically very good, and the mushroom's got good local structure. You've got this kind of remarkable set of reflections in the soap bubble. This, I don't know what it, latte or cappuccino, looks really delicious, and the food looks pretty good too. So it's really starting to capture a lot of good features of synthetic images. Okay. And here's the architecture of Big GAN. I'm not sure there's anything, it has upsampling blocks for the generator and downsampling blocks for the discriminator. You can probably look at it at your own leisure. I don't know that there's any particular lessons there. They did summarize, should be a summary slide with Big GAN's architecture somewhere. Um, all right, never mind. Okay, so last topic is evaluating GANs. I think this is the last topic. And so a challenge with evaluating them really is that let's see, what I want to, there are a variety of problems with the actual natural quality of the images. The discriminator might learn various sort of non-perceptual differences that don't matter very much, that occur with adversarial images, which we're going to talk about next time. So not everything that the discriminator learns is actually relevant for perception. So remember, the discriminator is kind of a universal classifier. It's not really like a human being. And our goal was actually to discriminate, in a way that a human would. So basically people looked around and said, well, are there a priori networks that are very good at classifying images in a similar way to a human being? And one of the networks that has proved to be the closest is one of the inception networks, Inception v3. So if you recall what the inception networks were, those are the networks that Google produced that have basically blocks of multi-resolution convolutions. So unlike a ResNet, which is very homogeneous and just lots and lots of 3x3 convolutions, the Inception had 1x1, 3x3, and 5x5 in parallel, if you remember. And that architecture seems to be closer to the human visual system. So inception networks seem to see the world more similarly to human beings. And that means that evaluations based on inception networks are quite good at evaluating the natural quality of an image. So let's see. Yeah, and in a bit more detail, so if we have this conditional classifier result from, we classify some sample X, we can compute a kind of marginal probability of the label by summarizing over all classifications. And then under this score, this inception score, it turns out that that a good GAN should have very low entropy for the conditional score P of y given X, but high entropy for the unconditional Y. So what does that mean? Well, it means that basically knowing the class of an image gives you a lower entropy, meaning that class label is more likely than the whole set of images. So in other words, if you take a set of all images, all classes that a given X could be, you would hope that a natural X would fit very well into one of the classes, like dog, cat. And if the natural image doesn't fit very well into a class, then it's probably not a very good natural image. So I hope that's somewhat intuitive. It probably requires a little bit of thinking through and reading the paper. But anyway, that's the idea. And empirically, it's been shown to correlate well with human estimates of quality. Okay. Yeah, it doesn't really, I mean, because the networks are typically trained on ImageNet or other large naturalistic image data sets, they don't really work on, say, cartoons or sketch images. Yeah, and again, the inception model seems to be a good approximation of the human perceptual system. So the scores from in the inception system, inception scores, tend to be correlating pretty well with humans. Okay, so a variation on this is the Frechet inception distance. It's based still on an inception network, but instead of just looking at output probabilities, you look at a certain function of the activations of fully connected layers in the output and compute this metric. And yeah, I'm not going to try to explain this one, but it is one of the better performing estimates, a little better than inception score in terms of modeling human classification. Okay, so actually, yeah, there is one more cool idea, which is trying to leverage different data sets for conditional image generation. So we've argued earlier that conditional generation is really important and useful. Usually want to generate an example of something that lies in a known class or that has a known label on it. So on the other hand, you don't always have nicely curated data sets describing objects and having labels. But very often we do have different data sets that are not paired of types of image. So you might have pictures of sketches of shoes and then actual images of shoes. They might be different sizes. Yeah, so actually, sorry, well, you could have that and they're not paired. That's actually shown here as being paired. You could have various paintings and various natural scenes, and somehow you'd like to use one of the natural images to produce a sort of corresponding synthetic image, but there's no alignment. So what do you do there? It still seems really useful because we have way more kind of just unlabeled, unmatched data sets in some domain. And it would be nice if we could just take one domain of images and another domain of images and just generate transformations between them. So probably a lot of you know about this. This is Alyosha Efros's work with various students. And yeah, basically you create a cycle, you close the loop with two generators and two discriminators. And basically, if you look back at what we've done so far with GANs, we also haven't really used paired images. We've used real and synthetic. In no sense is the real image or the synthetic image similar to the real one. With the conditional GANs, that was a little bit different, but basically in the cycle GAN, we use a cycle consistency loss for pairing, which is an L1 distance. And basically, so what we do is we go from some domain, some point X. We learn the conditional generator that takes us to Y. And it's some Y, right? It's some image that we've synthesized. And then we take it back again. Oops, keep losing the cursor. We transform it back again using the other conditional GAN. And so now we get a point back in our original space, and we only have to compare. Come on, cursor. We only have to compare in the X space to get a loss. And we want that to be small, right? You want it to be able to transform one way and then back again and get a similar image. Even though we don't know, we can't supervise it over here and say it should be this particular image in that domain. Doesn't matter because we're going to bring it back anyway. But we do want to minimize this loss here. And similarly, in the other domain, we start with some particular image of, say, a painting, transform it into the X domain, which is the real image domain, and then we transform it back again with the other conditional GAN. So now we're going to get, again, two images in Y, and we can directly compare their losses. And this works. It's probably not very intuitive, but it's working for the same reason that the normal GAN works, even though when you feed it, it never sees matched pairs of real and synthetic images. But what's happening here too is that this particular cycle GAN going from red to blue domain, from Y to X, it has to perform two tasks. It has to be able to successfully transform images from the synthetic images back again. It has to also transform real images into the X domain. And in order to do that effectively, it basically has to learn to correspond. I hope. All right, I hope everyone's hearing what I'm saying. I'm getting a warning about my internet connection. But anyway, I've got 2 recordings going, so hopefully you'll get the sound later on if it gets lost here. Okay. And so here are some of the amazing images that the CycleGAN has produced. And you can see, good. Okay, thanks for the feedback. Yeah, you can see that most of the time it does a remarkable job. It really had no supervision about the content, but you can see going from paintings to natural scenes, all the features line up, the geometry looks good. It's just working very well. You know, you can transform zebras to horses, summer to winter scenes. Let's see, yeah. There are just many examples of the sketches to real, to cartoon, etc. It's an extremely rich approach, pretty amazing work. And someone's asking, is it similar to neural style? Not really. I mean, it's very much more powerful than neural style. It's not, first of all, well, it shares something in common with neural style, which is that it doesn't require, well, okay, let me think carefully. I suppose that's a fair question. I suppose it does have the property that it didn't require aligned images, or am I right there? I have to think about that for a moment. It's computing moments. Yeah, I guess, all right. Well, in fairness, no, it does have the same property that doesn't require aligned images or paired images, because neural style typically works on statistics between of the moments of the some of the output layers. But it's very much more powerful, I would argue, in that, let's see, how can I put this? It's using discriminators that can, you know, compute a lot more than just moments. So the moments are good. They produce images that have some characteristics of the style target domain. But here, because you have a discriminator, it's going to produce a image in the other domain that's much harder to discriminate from a real example from that domain. So, you know, the natural images should look a lot more natural than neurally styled images. Neurally styled generally works really well for artificial domains, going from natural to artificial. It doesn't work too well going the other way. This method works really well, but going both ways. Okay, just a couple more things. XGAN, yeah. So it's a similar idea of consistency, using shared embeddings for both domains. And yeah, so you can see that you get some improvements from using that method. Okay, so let's wrap up. So to summarize, some advantages and principles of GANs. So the one major example is that they only need to generate samples of images P of X. They don't require modeling of probability distributions. And they take in general, for a general GAN, it's just taking a random latent variable Z and producing an X from it. They simultaneously train a discriminator that's very powerful in terms of critiquing or producing gradients that can be used to improve the image. The original GAN used the Jensen-Shannon divergence, which is still pretty good, but has some limitations. A variety of methods were used to improve that, including Wasserstein distance instead of JS divergence. A whole family of research focused on the generators themselves to try to improve them, and especially their kind of coarse-defined quality. And originally there was progressive GAN, but then big GAN was a simple architectural improvement that kind of subsumed progressive GAN and still used a coarse-defined architecture, but was able to produce really good images without the progressive training. Okay, we mentioned what WGAN already. And so in practice, there are many tricks. You've got to sort of manage the training if you're using normal GAN objectives so that neither player gets too far ahead of the other. And the papers, various papers contain a variety of tricks for improving things. So we'll stop there, and we'll see you actually, I think I'm sorry, it's either David or Roshan will actually be teaching on Thursday because I'm at the retreat. And I do have office hours today from 1 to 2. I think I sent that on Piazza, but I had to move them because of our grad student visit. So otherwise, we'll see you next week. Actually, I won't see you next week. It's spring break, so 2 weeks from today. Bye-bye.